On November 15th, physicist Michio Kaku announced an unprecedented scientific discovery related to the interstellar object ThreeI Atlast. Data from the James Webb Space Telescope suggests that within Atlast, or as part of its structure, there may exist complex biological activity. These signs include strange organic molecules, anomalous isotopic ratios, thermal irregularities, and notably chiral properties and bioluminescence, all of which defy explanation by known abiotic natural processes. More remarkably, Atlast appears to have altered its trajectory to remain within the solar system, and is now approaching Earth, raising urgent questions about the intent of this extraterrestrial life, and how humanity should respond. Coming up, we will delve into the hidden world inside Atlas through the lens of James Webb, and explore the careful inferences made by physicists in the face of this extraordinary event. The James Webb Space Telescope is now turning its attention toward ThreeI Atlast, an interstellar object that has never been mapped. And at that very moment, physicist Michio Kaku exclaimed that something appears to be alive inside ThreeI Atlast. Initial imaging through the NEOSPEC and MIRI instruments revealed a reflective structure that defied baseline expectations for cometary dust. Unlike traditional long-period comets, Atlas showed minimal coma diffusion, and instead emitted a tightly collimated spectral line indicative of a highly ordered surface composition. The NIRCam instrument corroborated the spectral anomaly with high-resolution snapshots of a hexagonal surface pattern shimmering in ultraviolet scatter. These weren't random reflections. The geometric symmetry was too precise to align with light vector orientation from the Sun changing subtly with the orbital arc. For 11 days, JWST maintained continuous observation, while auxiliary optical arrays from the Subaru telescope in Hawaii and ESA's Gaia observatory in L2 orbit joined in synchronized lockstep. The international coordination wasn't merely procedural, it was a direct response to a growing sense of scientific unease. The object wasn't just drifting, it was behaving. That behavior sparked a cross-consortium emergency session within the Planetary Defense Coordination Office (PDCO), prompting real-time data mirroring between agencies. Researchers at the Max Planck Institute noted that Atlast's light curve varied not with solar wind turbulence, but in response to solar angle suggesting reflectivity optimization. In effect, Atlas seemed to be modulating its signature. That was no longer just observation, that was interaction. In silence, it adapted intelligently or otherwise. By the 12th day, Atlast had entered its first perihelion window, slipping behind the solar curtain for 73 hours. And for those 73 hours, the Earth lost sight not of a rock, but perhaps of something far more deliberate. As the solar occultation ended and the full silhouette of ThreeI Atlast returned to the sensors, a new layer of complexity emerged across its surface, challenging every natural model previously used to classify interstellar bodies. Thermal maps revealed that Atlas carried a network of localized hotspots, arranged with a precision that mirrored engineered layouts, rather than random geological placement, each point maintaining consistent angular spacing relative to sunlight, even as the object shifted along its hyperbolic to elliptical transition. When JWST compiled the heat distribution over time, the pattern behaved less like cooling mineral strata, and more like a controlled system with heat rising and dispersing, in rhythmic intervals that suggested a circulatory or metabolic-like process happening under the visible crust. Further analysis deepened the puzzle. These heat signatures were connected by branching corridors of elevated temperature, reminiscent of vascular pathways, or distributed neural filaments forming a topology recognizable in biological networks rather than the inert rock. At the same time, spectroscopic data captured irregular carbon chains across Atlast's reflective panels, molecular structures whose biased chirality indicated selective synthesis instead of natural chemical drift, reinforcing the suspicion that these compounds did not arise randomly, but through regulated chemical pathways. The consistency of these anomalies shifted the interpretation of Atlast's identity. Instead of a silent cometary remnant, the object began to resemble an integrated system, responding dynamically to its environment, adjusting its thermal output with the precision of a feedback loop. Researchers observing long-duration scans noted a cyclical emission spike every 243 to 248 seconds, a narrow range too stable to be attributed to solar heating, and their internal reports increasingly refer to these pulses as functional signals rather than incidental noise. The deeper the scientific community looked, the more Atlast resisted categorization, presenting signatures that converged on a single implication-coordinated behavior. For the first time, Atlast was no longer being evaluated as a wandering mass of interstellar debris, but as a structured entity carrying within its geometry the early indicators of organization optimization and possibly agency, pushing the investigation into territory where biology, physics, and the unknown met without a clear boundary. In the days following its passage beyond the Heliopause interaction zone 3, ThreeI Atlast began displaying a set of behavioral anomalies that could not be attributed to inert celestial physics. The object's surface temperature began oscillating in tight sync with the local solar flux, not in gradual response as expected from cometary ice sublimation, but in sharp feedback curves that mimicked an anticipatory adjustment, almost as if Atlast was predicting its solar input and preemptively calibrating surface albedo. At first, researchers suspected a phase delay artifact caused by lag in sensor relays, but as observations accumulated across spectrums, X-ray, ultraviolet, thermal, infrared, the timing precision held within milliseconds across multiple observation platforms. Atlast was not reacting passively. It was engaging in an active thermoregulation strategy. Notably, when a burst of solar wind intensified near perihelion, Atlast's outer layer emitted a sudden plume of molecular hydrogen and carbon radicals, but only in the hemisphere facing away from the solar direction, implying a directional shielding mechanism that selectively released mass to maintain torque balance and avoid momentum destabilization. This ejector did not follow ballistic dispersion patterns, but instead formed a controlled arc curving away from gravitational vectors and trailing for kilometers in a coherent plasma strand. Atlast was not just shedding mass, it was shaping its wake. Over the next 48 hours, Earth-based observatories tracking polarization angles reported shifts in Atlast's reflective properties. Its surface darkened by 18% under increased photonic pressure, then brightened again after clearing the solar ecliptic. These changes could not be explained by dust coma fluctuations or rotation alone. They suggested active modulation of surface materials, possibly by reorienting reflective compounds or altering dielectric structures to counteract radiation load. Biologists in the interdisciplinary task force began raising the possibility that Atlast was demonstrating something akin to adaptive camouflage, though not for concealment, but for survivability in hostile environments. The working term adaptive index was coined, measuring the object's response, latency efficiency, and inverse entropy effect relative to solar radiation. Atlast scored 0.87, far higher than any non-biological system recorded. Meanwhile, the object's orientation began to subtly shift, not tumbling chaotically, as would be natural under irregular jetting, but through micro-adjustments that suggested torque vector control. Over the course of 6 days, its rotational axis aligned increasingly with its flight vector, a behavior consistent with minimizing drag or preparing for maneuver. When simulations were run backward, researchers discovered that the alignment process began hours before the first solar ejection, once again pointing to preemptive behavior. If ThreeI Atlast was anticipating solar events, then it was also mapping space-time conditions in real time and acting on them. The possibility emerged that the object housed an internal system, whether mechanical, energetic, or unknown, that responded to environmental variables not as a byproduct of composition, but as part of its fundamental operating design. Some speculated it was a shell of smart materials with memory properties. Others argued for a nested thermodynamic core capable of processing external inputs. Regardless, Atlast was passing the thresholds of passive interstellar drift and entering a new category 1 where survival in transit was governed not by luck, but by rule-based adaptation. For the first time in decades of cometary observation, scientists were forced to write new taxonomies. Not comet, not probe, not relic. Atlast was now being catalogued as a reactive entity with behavioral indicators and ReB classification reserved only for candidates exhibiting targeted response to astrophysical stress. That designation carried weight not just among planetary defense agencies, but among those tasked with assessing the implications of encountering an engineered intention-bearing structure. What began as anomaly had become profile. What looked like chance now resembled protocol, the silence of 3. Atlast, far from being emptiness, had transformed into something else, something responsive, something precise, and something that, if not conscious, was at least acutely aware of the space through which it passed. As ThreeI Atlast emerged from its first perihelion window, researchers across multiple observatories prepared for a second wave of data acquisition, this time focusing on spectroscopic and molecular analysis. With telescopes realigned and the infrared arrays of the Infrared Telescope Facility IRTF in Hawaii and ALMA in Chile reactivated, a barrage of high-resolution scans was launched within a 17-hour observational corridor. What they retrieved was confounding. The outer shell of ThreeI Atlast reflected not just volatile sublimation or standard carbonaceous dust, it bore absorption lines consistent with complex hydrocarbons. These weren't random molecular fragments from interstellar debris. They exhibited long-chain sequences including alkenes and traces of amino precursors, most notably ethylamine and glycolaldehyde compounds, heavily associated with prebiotic chemistry. The readings alone were rare, but what startled the chemical teams was the coherence. These compounds weren't diffusely scattered across the coma or trail. They were localized to structured points on the surface, forming regular emission intervals that seemed to correspond to the object's rotation pattern. As Atlast rotated, these molecular emissions pulsed in consistent cadence, like biological respiration or energy cycling. The Vera C. Rubin Observatory, through its rapid imaging spectroscopy mode, picked up spectral flickering at 247-second intervals, perfectly aligned with thermal shifts in Atlast's shadow-facing hemispheres. This modulation pattern didn't match any known cometary outgassing behavior. Instead, it resembled active thermal regulation. More anomalies followed. An unexpected spike in trace phosphorus was detected far beyond background cosmic concentrations. Phosphorus, while not unheard of in cosmic bodies, rarely occurs in free-flow molecular clouds. On Atlast, it appeared clustered in recurring hexagonal emission blooms matching the geometric tiling observed earlier by JWST. The elemental clustering triggered intense debate among biochemists. Some argued it might be evidence of a primitive scaffolding system, akin to protein folding zones in early ribosomal simulations. Others remained skeptical, citing the risk of anthropomorphizing random mineral patterns. But as Atlast continued to pulse, its molecular signature doubts eroded. One of the most controversial signals came from a sharp methane-nitrogen burst captured by the European Extremely Large Telescope. Instead of degrading randomly, the burst split into dual lobes mirroring on opposite axes. The mirrored flow resembled a form of bilateral chemical processing, a hallmark of adaptive systems, potentially even metabolic. Atlast, once thought inert, was emitting signs not just of complexity, but of systemic control. As data poured into central analysis nodes at NASA's astrobiology program and ESA's ExoLife Watch network, a question began to surface not just in scientific journals, but within classified panels. Were these emissions accidental, or was Atlast signaling? The word biosignature was initially banned from internal memos deemed too speculative, too inflammatory. But the pattern continued. Spectral echoes from Atlast's emissions began to show periodic modulation at 29.3 second micropulses, falling within radio frequency harmonics used in adaptive scanning systems. The pulses repeated, and then paused, and then began again, offset by 0.3 seconds as it crossed its nodal tilt. This was not noise, it was message or mimicry, or both. The larger community didn't reach consensus, but a splinter group within the Lunar and Planetary Institute drafted an internal hypothesis. Atlast was a modular organic matrix capable of adaptive chemical feedback, possibly seeded, possibly reactive, but unmistakably organized. ThreeI Atlast no longer stood as a passive body drifting through space. It behaved as a system, coherent, iterative, and subtly aware of its stellar context. What it was adapting to remained uncertain. But the data made one thing clear: ThreeI Atlast was not alone in its own evolution, and now Earth was part of its biochemical equation. As the molecular composition of ThreeI Atlast continued to baffle analysts, a new layer of complexity emerged, this time from its inherent spatial symmetry. Spectroscopic analysis from the ESO's Very Large Telescope and the James Clerk Maxwell Observatory converged on a startling discovery. The light reflected from specific emission arcs on Atlast was not just polarized, it displayed chiral rotation. At first, the measurements were dismissed as sensor noise. Chiral polarization, or optical activity, is a trait usually reserved for complex biological molecules, left-handed or right-handed configurations that twist light in distinct directions. But follow-up analysis confirmed it. The isomeric shift was real, stable, and repeated across multiple observation windows. ThreeI Atlast was producing optically active compounds. What was more unsettling was the imbalance. Instead of a random mixture of left-handed L and right-handed D molecules typical of abiotic chemistry, Atlast exhibited a strong bias toward one enantiomer. The L-form amino precursors in particular dominated by nearly 94%, a percentage eerily reminiscent of homochirality in Earth-based life systems. The molecular clusters emitting these signals were not isotropic. They lined up along Atlast's hexagonal fault lines, forming mirror-split crescents that rotated in counterphase across its equator. Each wave of polarized emission traced a pattern as if ThreeI Atlast was projecting a spatial code into space. From a physical perspective, symmetry in inert bodies is expected, but ThreeI Atlast defied that norm. Its asymmetry was neither random nor chaotic. It was structured, persistent, and reactive to solar vector shifts. As it tilted along its orbital plane, the chirality of emitted molecules oscillated, suggesting some internal compensatory system, a feedback loop between surface chemistry and incident radiation. The implication sent shockwaves through theoretical biochemistry teams. Chiral dominance in a non-Earth, non-solar system object demanded explanation. Was this the fingerprint of selective synthesis, or the fossil residue of a metabolic system? Either way, Atlast now bore another trait once thought to belong solely to life: molecular handedness with intention, and it was handing us a puzzle that spanned light symmetry and something deeper, perhaps even designed. 3. Atlast exhibited more than just molecular peculiarity. It radiated heat in pulses that didn't align with solar heating profiles. While most celestial objects reflect thermal energy in predictable gradients, Atlast's emission spikes followed a rhythm, as if its surface responded dynamically to solar flux, not passively, but with calculated modulation. Thermal mapping from both the James Webb Space Telescope and the ALMA array revealed a segmented latticework along Atlast's subsolar ridge. These segments displayed alternating bands of high and low thermal inertia, arranged in a hexagonal grid-like formation. Even stranger, this network evolved over time, not just warming but reconfiguring. The hot zones migrated longitudinally as Atlast approached perihelions, suggesting a distributed energy regulating system. Unlike typical cometary surfaces which retain heat or radiate it erratically, Atlast appeared to channel energy along discrete pathways. These thermal veins followed non-random topologies, concentrating heat dissipation near polar vents that coincided with jets of molecular vapor. That coordination raised a critical question: was this behavior emergent or engineered? One hypothesis gained traction. Atlast was mimicking a nervous system at scale. Each thermal node responded to solar input with delayed but purposeful shifts, like bio-inspired thermoregulation. The way heat was not merely absorbed but routed suggested feedback, a mechanism akin to thermal homeostasis. Adding weight to this was the presence of phase-shifting compounds. These were not simple ices. Some crystalline forms detected in Atlast's plume exhibited reversible phase transitions near 120 K, a range tailored to Atlast's orbital environment. These materials acted as thermal buffers, absorbing excess energy, then releasing it gradually as if dampening internal stress. Researchers began referring to it as a bioanalogous thermal net. It was not alive in the biological sense, but it behaved like something that had learned how to survive. More than insulation, this system maintained chemical viability under deep space extremes. The synchronization between thermal rhythms and molecular ejection hinted at a master process, whether of natural complexity or artificial design. ThreeI Atlast wasn't just reacting to the sun, it was managing itself against it, and somewhere within its shifting heat map lay a design that blurred the line between comet and construct. Among the many scientific puzzles ThreeI Atlast presented, one anomaly stood out with quiet defiance: its isotopic ratios. Spectrometric breakdowns from both Earth-based and orbital instruments revealed a nitrogen-15 to nitrogen-14 ratio that deviated significantly from solar system norms. More than a statistical outlier, this isotopic skew mirrored distributions previously theorized for prebiotic zones in interstellar molecular clouds regions, where organic synthesis is possible, but life is not yet assured. Further deep analysis of carbon isotopes compounded the enigma. Atlast's carbon-13 presence was not only elevated, it formed consistent clusters around molecular structures associated with amino acids and formaldehyde derivatives. These were not fragments of random chemistry. They were structured, bounded, and echoed patterns seen in meteorites considered to hold the remnants of ancient biotic material. The oxygen isotope profile was even more provocative. It did not reflect a natural fractionation from solar formation, but suggested exposure to heavy UV-driven photochemistry in environments far older and colder than the Oort cloud. These ratios weren't just chemically distinct, they were narratively charged. They whispered of processes that predated the solar system, possibly even processes guided by selective chemical evolution. If these molecules had formed in a cradle far beyond our planetary nursery, then ThreeI Atlast was not a visitor merely from another star, but from another evolutionary arc. A faint question emerged in the background of data. Were we staring at a molecular fossil? A relic of life crafted, selected, preserved, travelling across star systems not by chance but by function? And if so, was Atlast the message or the messenger? As ThreeI Atlast pierced deeper into the inner solar system, its spectral fingerprint began to shift. Ultraviolet and visible band observations captured by the James Webb Space Telescope revealed a series of emission spikes that didn't correspond to any known atomic transitions. These weren't solar reflections nor thermal echoes, they were active emissions pulsing at semi-regular intervals, suggesting a mechanism of energy release embedded within Atlast's core composition. The most startling discovery came when these emissions aligned with specific wavelength bands often associated with bioluminescent processes on Earth, particularly marine organisms that use luciferin-luciferase reactions. But in the case of Atlast, the glow didn't come from any thermal source or known exothermic reaction. It emerged in cold zones far from the solar-facing hemisphere. Deep spectral deconvolution pointed to unidentified polycyclic compounds, large ringed molecules with extended pi electron systems, some of which bore resemblance to porphyrin structures involved in biological light emission. These compounds were stable, non-volatile, and activated only under specific flux densities of solar radiation, suggesting some form of light-triggered photoluminescence. What raised further intrigue was the consistency of this glow. It didn't fade with solar distance, nor did it fluctuate chaotically. Instead, it pulsed with Atlast's rotation like a signal encoded into the body's own spin. These rhythmic pulses traced across its surface like a heartbeat made of photons. Some observers dared to ask, was this a biological remnant, or an engineered luminescent system meant to signal, perhaps even to navigate? ThreeI Atlast glowed not with chaos but with cadence. It wasn't just reflecting the sun, it was sending light back into the void as if expecting someone or something to notice. As the various observatories and probes aligned their findings, a coherent image of ThreeI Atlast began to form, not as a passive rock adrift through interstellar space, but as a dynamic reactive body. Each fragment of data, once dismissed as an isolated curiosity, now fit into a larger unnerving pattern. The hyper-reflective jets observed during perihelion weren't random. They were aligned with solar flux peaks. Atlast's non-gravitational acceleration, previously explained away as asymmetric outgassing, instead followed a mathematical periodicity, responding not to solar heat but to gravitational gradients between planetary alignments. This suggested a responsive control-like behavior, not chemical chaos. The organic compounds, some of which showed chirality and biogenic-like carbon ratios, were embedded within a matrix that shielded them from radiation decay. Their stability over long durations hinted at design, not accident. When viewed in isolation, these facts were anomalies, but synthesized they painted a portrait of intention. Atlast's rotational pulses, its isotopic asymmetries, its spectral emissions all followed internal harmonics. Like a song meant to be heard across space, the object seemed to broadcast not just data, but pattern. From the outer solar system to its closest approach, ThreeI Atlast displayed a behavioral chain, one that escalated in complexity then receded. It activated, revealed, responded, and then abruptly went silent again. Some analysts began to whisper comparisons to Oumuamua, but others insisted Atlast was no twin. This was an organism of design or a device of purpose, and now, standing at the intersection of chemistry, trajectory, and intention, the question no longer was whether Atlast was special. The question was whether we had missed its message entirely. As the analytical teams cross-referenced data from ultraviolet radio and mass spectrometry instruments, a quiet question began to form, one that had haunted exobiology for decades. Was this body simply reacting to physics, or had it been shaped to sustain life? 3. Atlast was no ordinary interstellar object. Its surface bore the signatures of selective shielding carbonaceous layers that resisted both ionizing radiation and micrometeorite impacts. Deep beneath those outer layers, transient heat pockets were detected zones where internal temperatures surged and stabilized, periodically defying the expected thermal decay of a cometary nucleus. These warm cavities hovered within a range theorized to support biochemical processes, particularly extremophilic microbial activity. But Atlast's anomaly didn't stop there. Inside the ejected materials, near perihelion researchers identified amino acid analogues with consistent L-chirality, a feature almost exclusive to Earth-origin biochemistry. Even more puzzling were traces of phosphorus-laden chains exhibiting reactivity under solar UV but degrading under artificial light, as if tuned to natural stellar conditions. These chains bore resemblance to primitive RNA scaffolds, yet were stable beyond terrestrial models. Was this the footprint of life, or an engineered mimicry of its conditions? Some theorists lean toward panspermia, suggesting Atlast might be a dormant vessel carrying seeds, not systems. Others pointed to its non-random activation sequence thermal pulses before acceleration spectral emissions timed with planetary conjunctions and a shutdown precisely at observational blind spots. That choreography hinted at more than survival. It hinted at awareness. ThreeI Atlast did not present life as we knew it, but it mirrored life's logic, adaptation, protection, signaling, and internal structure. It operated within environmental margins long believed inhospitable, yet suspiciously close to extremophile thresholds. As Earth looked on, Atlast forced an uncomfortable redefinition. Perhaps the question wasn't whether there was life out there. Perhaps the question was whether life in some form had just passed us by, measured, contained, and unrecognized. As the international astronomy community reviewed the data cascade from ThreeI Atlast, expert interpretations began to diverge, yet none could ignore the underlying pattern. The structure was too precise, the timing too refined, and the energy signatures too deliberate to dismiss as mere cometary coincidence. Spectroscopists pointed to the rhythmic emissions as indicators of programmed decay or energy release. Rather than following random outgassing Atlast signals, maintained a steady periodicity enough to prompt discussions around autonomous systems, even self-regulating ones. Some drew parallels to pulsars, though no neutron star ever moved this close or this slow. Thermal imaging specialists highlighted Atlast's ability to retain and channel heat along certain axes like conduits or vents. These regions didn't align with sunlight exposure but with its rotational rhythm. It was as though Atlast was sculpted to breathe in taking solar energy and redistributing it in controlled waves. Astrobiologists, meanwhile, saw patterns too familiar to be ignored. The layering of carbonaceous shells, the presence of complex organics, and the isotopic gradients all hinted at deliberate preservation, perhaps even an incubatory function. While most refrained from open declarations, their internal memos spoke of cautious astonishment. The word designed appeared more than once. Among the few who spoke publicly, Professor Lena Chen of the Vienna Astrophysics Institute summarized it best. "We're seeing consistency where we should see chaos. This object behaves like a system, not a relic." It was no longer just about what Atlast was. It was now about who might have once engineered or deployed it, and whether Earth had just witnessed the ghost of a logic far older than its own. When ThreeI Atlast entered the observable zone of the solar system, orbital analysts expected it to follow a hyperbolic trajectory consistent with other known interstellar visitors. Yet within days of trajectory, plotting residuals began accumulating subtle, then undeniable. Atlast wasn't simply passing through, it was deviating slightly but persistently from every gravitational prediction. Initial models calibrated to barocentric coordinates, and solar-wind interactions failed to hold. The object's motion introduced a drift vector that seemed non-random, resisting solar perturbations rather than yielding to them. Calculations done using standard JPL horizon solutions reported increasing errors in right ascension errors that grew with time, not shrank with refined data. It was as though Atlast had intentions, like it was correcting or rebalancing in response to some unknown frame of reference. The anomaly intensified near perihelion. While most bodies accelerate following Keplerian mechanics, Atlast slowed, then regained speed at a moment inconsistent with any predicted solar maneuver. This phase shift, minor in delta V, but major in implication, prompted orbitalists to revisit Oumuamua's trajectory for comparison. But Atlast's deflection wasn't a one-time burst, It was incremental, layered across time like microthrusts. Some suspected sublimation or gas jets. But no tail behavior corresponded to the vector changes. The jets, when they appeared, were orthogonal, not reactive. Solar pressure couldn't explain the consistency. Radiation modelling showed no sufficient torque to cause rotational precession that matched the drift angle. The motion violated all known passive comet models. That's when the term non-gravitational acceleration re-emerged first, cautiously, then pervasively. It had been used with Oumuamua, but here it wasn't just an epicycle of explanation, it became the defining variable. Atlast appeared to respond not just to the Sun, but to something else, perhaps an internal map, a destination, or a feedback loop invisible to current instruments. As more data arrived, the errors in predictive modelling reached a threshold where new simulations had to assume intelligent revectoring. Not guidance in the human sense, but course adjustments like route corrections. Some called it inertial buffering, others hinted at stored momentum, a few simply admitted defeat. For the first time, trajectory wasn't just about gravity, it was about intent. 3I Atlast wasn't drifting, it was navigating. 3I Atlast did not drift into the solar system as a passive object. From the earliest reconstructions of its inbound trajectory, analysts noticed something off-pattern, instead of plunging through interstellar space with a chaotic vector. Atlast approached the heliosphere at a highly optimized slant, skimming the gravitational influence of the Sun in a way that maximized acceleration while remaining within the ecliptic plane. It was a controlled maneuver, not a cosmic coincidence. Data compiled from the James Webb Space Telescope ALMA and the mid-infrared sensors aboard SOFIA revealed micro-adjustments in its velocity vector, starting well before it crossed the Kuiper belt. These shifts weren't random. They occurred at repeating intervals, subtle nudges that seemed both deliberate and effective. What made them extraordinary was the absence of any visible outgassing or reaction mass, a complete lack of natural propulsive mechanisms. Yet the trajectory changed minutely, but purposefully, suggesting navigation rather than drift. When 3I Atlast approached the orbit of Jupiter, simulations predicted significant gravitational interference enough to alter its course drastically. But that never happened. Instead, Atlast bypassed the gas giant with surgical precision, like a spacecraft plotting to avoid a gravity trap. The maneuver defied the expectations of every standard celestial model. Further down the trajectory as Atlast passed into Earth's shadow cone, where optical surveillance systems temporarily lose tracking due to solar interference, an anomaly emerged from ESA's radar network. A faint vector deviation was recorded, small but directional, as if the object had made a conscious angular correction to slip past a satellite positioned in geostationary orbit. It wasn't evasion by luck, it was tactical. This behavior became a pattern, not frequent enough to raise alarms, but consistent enough to avoid pure coincidence. Aerospace analysts began drawing parallels to low reflectivity techniques used in electronic warfare, soft signal jamming, stealth bypasses, maneuver masking. These were not traits of a comet. They were tactics. Tactics required either intelligence or instruction. 3I Atlast was not merely moving, it was responding. This gave rise to a controversial but unavoidable inference: Atlas might possess some level of agency, either onboard or external. It was not being guided by gravity alone, it was choosing its own path. Not just avoiding obstacles, but actively minimizing exposure. Not revealing itself in full, but showing just enough to be detected and questioned. The idea of intentionality shifted the narrative from scientific anomaly to strategic presence. Was this object hiding, watching, or testing us? The community hesitated to say it out loud, but the thought was undeniable. If these flight corrections were intentional, if the approach vector had been optimized from interstellar space, then 3I Atlast was not just visiting, it was approaching with a reason. The sum of anomalies surrounding 3I Atlast began to exceed what natural randomness could explain. Each directional shift, each evasive maneuver, and each timing precision taken alone might suggest chance. But collectively they formed a pattern, coordinated non-ballistic movement, indicative of trajectory management. Unlike other interstellar visitors such as Oumuamua, which coasted inertly through gravitational wells, Atlas demonstrated controlled approach dynamics, acceleration, timing, and avoidance behavior. Its flight path was not only efficient, it was adaptive, adjusting course, without visible cause, always optimizing position relative to planetary fields and sensor lines. The hypothesis emerged not from sensationalism, but from repeated modelling. What if ThreeI Atlast was not a passive body but a directed object, that it may contain internal guidance systems autonomous or remote, or even operate with intent? Its trajectory wasn't just unusual, it was structured, and structure in this context implied engineering. The possibility reframed the investigation. Atlast was no longer merely a scientific curiosity, it was now the centre of a hypothesis few dared articulate fully, that something or someone might have sent it. The mystery deepened not by what Atlast did, but by how consistently it did it. This was no accidental wanderer, it behaved like a scout. By the midpoint of the investigation, a fundamental shift had occurred in how ThreeI Atlast was being conceptualized, not just as a singular anomaly, but as a branching narrative with multiple plausible realities. The object's trajectory composition and reactive behaviour no longer aligned with any single known category of celestial phenomena. As analysts across agencies consolidated the mounting data, three major interpretative frameworks began to emerge, each distinct in implication, yet none fully dismissible. The first scenario classified ThreeI Atlast as an ultra-anomalous natural comet one that defied prior models due to a convergence of rare but natural astrophysical processes. According to this view, the non-gravitational acceleration could be explained by an exotic sublimation pattern, perhaps involving volatile compounds not yet catalogued or driven by exposure to high-energy solar emissions that triggered asymmetric outgassing. This scenario required the fewest new assumptions yet demanded belief in an almost statistically impossible combination of natural forces. Its supporters pointed to the object's irregular jet emissions and proposed that internal reservoirs of hypervolatile materials shielded by crustal anomalies might account for the sudden directional thrusts observed post-perihelion. But even among conservative theorists, discomfort lingered. Too many variables had to align perfectly. It was, in their own words, the least unlikely natural explanation. The second hypothesis treated Atlast as a derelict or remnant of alien technology, not active, but not entirely inert. In this framework, the structure was interpreted as a non-functional artifact of artificial origin, perhaps a probe, a scout, or a segment of a greater interstellar construct no longer operational. The presence of modular symmetry, geometric anomalies, and spectral reflections inconsistent with mineralogical expectations lent some support to this idea. Data suggesting internal cavities and multi-layered shell architecture hinted at possible internal compartments once functional, now decayed. The jets could be remnants of engineered propulsion systems degraded by time or exposure. This theory also explained the highly coordinated orbit corrections as residual programming or self-stabilizing systems reacting to gravitational vectors. Unlike the first scenario, this hypothesis accepted that the anomaly wasn't due to nature's creativity, but to technology's entropy. In this telling, Atlast was a ghost. The third and most controversial scenario proposed that ThreeI Atlast was a functioning interstellar entity, either autonomous or remotely directed and active craft, operating with real-time awareness of its trajectory and environment. This view, initially dismissed by many in the scientific establishment, had gained traction not through sensationalism, but through process of elimination. The precise timing of Atlast's solar approach, the coherent coordination of its perihelion maneuvers, and the strategic alignment with planetary orbital planes all resisted naturalistic modelling. Its non-random dimming patterns, its spectral emissions outside the expected solar reflectivity range, and its silence during critical observation windows suggested control, not coincidence. If Atlast was alive, technologically or otherwise, it had chosen when and how to be seen. Its route, including the gap event behind the Sun, echoed patterns seen in proposed orbital maneuvers like the Oberth effect techniques theorized for interstellar propulsion. For believers in this scenario, Atlast wasn't merely a traveller, it was a visitor. Each hypothesis carried its own emotional and scientific gravity. The first scenario preserved normalcy but stretched it to the edge. The second teased at an ancient history of cosmic exploration, one we might have just stumbled into the ruins of. The third confronted humanity with an unthinkable possibility that we are not alone and that contact may already be in progress not through beacons or messages, but through presence. Crucially, none of these scenarios could yet be proven or ruled out. Instead, they coexisted like overlapping layers of a puzzle not yet solved. Analysts began to refer to this phase as the triple collapse point, where all lines of reasoning converged but refused to simplify. The tension didn't lie in the lack of answers, but in the abundance of implications. Each theory rewrote the narrative in its own way, and the final determination would depend not just on more data, but on how willing Earth's scientific community was to ask questions it had long avoided. 3I Atlast had fractured consensus not because it was inexplicable, but because it was almost explicable through three lenses each whispering a different truth. As the directed object hypothesis gained credibility, a new question surfaced, one not of science but of protocol, if 3I Atlast was truly an engineered entity should humanity respond. In secure discussions across observatories, defense agencies and academic circles, the issue fractured communities. One camp argued for transmission, a directed signal encoded with benign intent, a universal handshake across the cosmic void. The opportunity to initiate contact they believed was a singular moment in civilization's arc. Silence in their view was a betrayal of curiosity. The opposing camp warned of catastrophic risk. If Atlast was observing, or worse evaluating, then a signal might reveal Earth's location, technological status, or vulnerabilities. Historical analogies from Earth's own colonial past were invoked. Contact does not guarantee diplomacy. And then there were those who questioned whether Atlast was waiting to be answered at all, or simply passing through, never meant to be intercepted. In this quiet, the debate remained unresolved. Across global networks, a decision loomed not of capability but of philosophy. Should we speak, or should we listen? And for now, humanity chose neither. It watched. As the anomalies surrounding 3I Atlast accumulated, formal assessments began to emerge from the world's most authoritative agencies. The SETI Institute was first to release a cautious briefing, emphasizing the need to distinguish between natural and artificial signal patterns. Their analysis confirmed that Atlast's electromagnetic profile contained irregularities, narrow band bursts and anomalous radio transients that merited further observation, though they stopped short of attributing intent. Meanwhile, the European Space Agency focused on trajectory and structural data. Their orbital reconstructions showed a course deviating from classical Newtonian expectations, particularly during perihelion, where gravitational slingshot effects failed to account for Atlast's altered arc. Internally, ESA analysts raised concerns about energy sources none were detectable, yet directional changes persisted. The implication: propulsion without emissions. NASA, typically measured in tone, released a technical bulletin acknowledging 3I Atlast's non-standard behaviour. Their deep space network recorded fluctuations in reflected light that couldn't be linked to natural outgassing or dust fragmentation. Most striking was the object's structural coherence. While comets and asteroids tend to exhibit irregular mass shedding, Atlast remained visually intact under extreme solar stress. Though none of the agencies declared Atlast artificial, their language had shifted from denial to ambiguity, from anomaly to possibility. A silent convergence was forming. Atlast defied categorization. It no longer fit known models, and that perhaps was the loudest signal of all. As 3I Atlast continued its trajectory through the inner solar system, a new phase of global surveillance was launched. No longer a passive subject of distant telescopes, Atlast became the focus of intensified, coordinated observation. Agencies around the world recalibrated their assets. The James Webb Space Telescope, having already provided initial data on its reflectivity and jet structures, was reassigned to intermittent high-resolution captures. Meanwhile, Earth-based facilities including ALMA Arecibo surrogate systems and ESA's deep space antennas were aligned for synchronized sweeps. Early data during this phase yielded contradictions. Spectroscopic readings revealed sudden alterations in the ultraviolet and infrared bands. A chemical signature, first assumed to be residual cyanogen, fluctuated in a way inconsistent with decay patterns of cometary nuclei. Furthermore, the ion tail of Atlast, rather than trailing behind it, began to drift at unphysical angles relative to solar wind vectors. These observations did not merely challenge pre-existing models, they invalidated them. More disturbing were temporal anomalies. Between observation windows spaced 14 hours apart, Atlast's visible jet orientation shifted by nearly 26 degrees without correlating positional torque. This raised urgent questions about internal control systems or active stabilization concepts alien to celestial debris. Some researchers postulated rotational precession, but the spin rate when recalculated was too stable. A critical transition occurred when the enhanced network began observing regular photonic pulses from Atlast's nucleus. These flashes, precise and occurring in intervals of 247 seconds, repeated over 3 cycles before stopping. Their wavelength distribution suggested no natural mechanism of production, leading analysts to consider intentional emissions. Though cautious, the SETI consortium quietly logged the event as a non-random temporal anomaly. Emotionally, the community stood divided, excitement shadowed by uncertainty. Some feared premature conclusions. Others whispered that something had just blinked back. Whatever ThreeI Atlast was, it had now become something more than observed. It had become observant. Following the anomalous pulse emissions from ThreeI Atlast, the global scientific response entered its second operational phase, the theoretical construction of a standardized outbound message. Unlike previous contact efforts aimed at generalized extraterrestrial intelligence such as the Arecibo message or Voyager's Golden Record, this effort focused on formulating a signal precise, concise, and technically decipherable by an unknown entity already exhibiting structured emission behavior. The urgency of this phase was amplified by statistical modeling. AI-assisted pattern analysis revealed an uncanny symmetry in the 247-second intervals, too precise for stochastic fluctuation, too deliberate for mere cosmic coincidence. With that data in hand, attention shifted from passive surveillance to calculated response strategy. The fundamental question shifted from what is it to, can it understand us? A working group led by SETI and supported by interdisciplinary teams from MIT, JPL, and ESA began reverse engineering signal templates optimized for universality. Binary encoded prime sequences were tested, as well as image compression into hydrogen line frequency modulations. The core idea: construct a message rooted in natural laws, mathematics, atomic structure, gravitational ratios that any sentient civilization would also observe. But with ThreeI Atlast showing unexpected photonic emissions and structural anomalies, the risk was clear: send too much and risk provocation. Send too little and risk being ignored. This wasn't just astrophysics. It was first contact diplomacy conducted at interstellar distance, with no feedback loop guaranteed. Psycholinguists joined the effort, proposing patterns of semantic symmetry that might indicate self-awareness in return signals. Meanwhile, engineers debated timing. Should the message be sent during Atlast's solar transit, when its shielding might be compromised, or in the weeks before its Earth-farthest trajectory? Behind the scenes, classified briefings emerged from military space agencies requesting veto rights over any outgoing transmission. Their concern wasn't scientific, it was strategic. If ThreeI Atlast was a probe, then any reply was an act of disclosure. Thus the second phase ended not with consensus, but with a prototype, a message encoded in hydrogen spin resonance patterns, structured in Fibonacci timing loops, and approved for silent activation pending further signal from Atlast itself. The world waited. ThreeI Atlast remained silent, but its silence no longer felt passive. While scientists debated frequency modulations and diplomatic payloads, a different kind of urgency unfolded below Earth's ionosphere among its people. The third phase of global response to ThreeI Atlast revolved not around data but perception. It was no longer about what humanity knew, but how it felt. The moment word of Atlast's anomalous behavior reached mainstream media, its coordinated jet structures, the photonic asymmetry, the mysterious signal pulses, the narrative broke containment. Social networks fractured into polarized streams: wonder, awe, fear, denial. Some believed it to be the long-awaited first contact. Others feared a hidden threat. A fringe minority insisted the object was a classified Earth-made technology. The truth stripped of consensus had become radioactive. Government communication channels struggled to maintain coherence. NASA's public statements remained cautiously neutral, referring to Atlast as an interstellar body of interest. ESA released technical updates, but withheld commentary on the biological implications of molecular data. SETI, for its part, began a series of live streams designed to educate, not inflame. Yet the silence from major geopolitical actors, Russia, China, and several military agencies only deepened the atmosphere of distrust. Psychological impact models developed in partnership with the WHO and international behavioral labs predicted a range of possible outcomes. Mild public anxiety was expected. But by week 2 of sustained Atlast coverage, real disruptions emerged. Markets showed volatility. Conspiracy narratives surged. Religious leaders called for prayer or warned of deception. In cities from Seoul to São Paulo, citizens gathered not in protest but in vigil. A particular complication emerged: the ontological shock, the destabilizing psychological effect of confronting evidence that contradicts one's worldview. For some, it was liberating. For others, it was paralyzing. and for many it triggered a quiet existential recalibration. If 3I Atlast was intelligent or even designed, then humanity's place in the universe had already shifted. Crisis communication experts began recommending soft disclosure tactics, analogies to past scientific revolutions framing the event as an opportunity for unity, not dread. Yet these efforts met resistance. The truth, however, softened, refused to be domesticated. The phase closed with a paradox: humanity had never been more connected, yet never more uncertain. The skies were watched. The feeds refreshed hourly, and through the static of a million screens 3I Atlast continued its silent passage, seen but undecided.